Hi, in this lecture video, we'll be talking about the equivalent load method and how the load balancing method can be used for the design of the prestressed concrete beam. In the last video, we saw the different stages of the stresses in the prestressed concrete beam. The first one is the stress condition when only the pre-stressing force is being applied. And as you can see, there is a large compression stress at the bottom and the small compression stress at the top due to the pre-stress alone. And now as we go on increasing the external moment and the external load, the tensile stress at the bottom due to the bending of the beam will keep on increasing. And at a certain point, the stress at the bottommost fiber of the concrete will become zero. And this moment, this external moment that causes the bottommost fiber stress zero is called as the decompression moment. And as we further go on increasing the external load and external moment, the tensile stress will start to develop at the bottommost fiber, and at certain point when the stress at the bottom is equal to the tensile strength of this concrete, the concrete will start to crack, and that moment where the concrete starts to crack is called as the cracking moment. So these are the two important stages of the prestressed concrete beam. But apart from that one, there is another interesting stage during this different stages, and that is called as the balance stage. In this balance stage, at certain amount of external load, the stresses in the concrete beam becomes uniform. That means at certain amount of external moment, the stresses becomes purely compression stresses and given by P over the force divided by AZ, the gross external area. So we know that the bottommost stress in the prestressed concrete beam is given by P over AZ, which is the uniform compression stress due to force P, plus the bending stress caused by the eccentricity of the prestressing wires and the bending stress caused by the external load. So if it is to be equal to uniform compression stress as at the balance point P over AZ, this will cancel out. That means that the balance moment M balance is equal to the prestressing force multiplied by E max. So what it means is that we can find out the prestressing force P and the eccentricity E in such a way that the beam is subjected to uniform compression stage at that external load. So the advantage of that one is that when the beam is subjected to uniform compression stress, there will be no deflection and there will be no cracks as well. So we'll be aiming for this balance stage at the normal work conditions of the beam. Now let's say for this beam, this is the centroidal axis and your pre-stressing wire is at the centricity of E max at the center, and the pre-stressing force applied here is P. Now let's say the external load is acting on the beam. So now this external load is W balance. Say at this point we are aiming to find the load that will give the uniform compression stress in the beam. So the moment M balance due to this uniformly distributed load of W balance is L square by 8, where L is the span length of the beam. Now we already saw that for the balance moment is equal to the pre-stressing force multiplied by P max in the previous equation. So equating this to W balance L square by 8 is equal to P multiplied by E max, which will give us W balance equal to 8 . So it means that when this external load W balance kilonewton per meter is applied on the beam will have no deflection and no bending stresses, because only the uniform compression stress is acting on this one. So this is the same thing as before, the stress analysis that we talked before, but it is looking from the load perspective, and this is called as equivalent load composite. So we are looking at the same thing, but we are looking more from the load perspective. So the equivalent load concept is that it is just an alternative approach to evaluate the effect of pre-stressing forces. So we will be talking about the loads that are acting on the beam due to the pre-stressing forces and how that will affect the performance of the concrete beam. And it provides the easy way to design the beam through the load balancing concept. So in the equivalent load method, we first, as I said, will be calculating the forces exerted by the pre-stressing tendon on the concrete, and we evaluate the effects of this one. And these forces exerted by the pre-stressing tendon on the concrete is called as equivalent loads. And the pre-stressing force exerts the forces on the concrete at either at the anchorage points or at the points where cable changes the directions. So at these points, the pre-stressing tendon will apply the force on the concrete. So now we are looking the same problem from the load perspective. So we are calculating the load that the pre-stressing tendons will apply on the concrete, and we use this one for the design purpose. Now first, let's look at the anchor side where the force is being transferred to the concrete. Say if the cable that we have here is so this is the anchor point, and our cable is parabolic or the curved profile like this one. So the forces that is applied here is at inclined direction as this one. The force P, that is the force, is transferred from the pre-stressing tendon to the wire to the concrete. So this force P is acting at an angle of theta, which can be resolved in the horizontal component and the vertical component. And for a small angle of theta, P cos theta will be P, and P sin theta can be simplified to P theta. So we have these two forces acting on the concrete from the pre-stressing tendon, P horizontal force P and the vertical force P theta. Similarly, for the pre-stressing tendon, which has the eccentricity of E, we still can resolve the forces into vertical and horizontal directions. So there is a horizontal force P acting at the point, and the vertical force P theta acting at the point, and these forces are acting at the eccentricity of E. Now if we have cable arranged in the profile as shown here, so if we have a pre-stressing cable arranged in this profile, let's see how the forces will be transferred to the concrete. So the first part, the force will be transferred to the concrete at the anchors here, and this is the force transferred to the concrete, and as I said, it can be resolved to the horizontal and the vertical component. So that is one point, and the force will be transferred at this point as well, and also the forces will be transferred to the concrete at the kinks as well. So at these points where there is a change in direction, so the forces will be exerted on the concrete from the pre-stressing tendons. So as you can see here, at this point at the kinks, the pre-stressing forces are P, which are acting at the angle of theta, and the force F is acting from the concrete to the tendon, and same reaction will be acting on the concrete from the tendon as well. So the reaction force F will be given by at the kings, the reactive force is given by the vertical component is P theta, the vertical component of this P theta, and you plug in the value as theta here. So as you can see here, the cables are arranged in such a way that this angle is theta, and at that point your eccentricity is E naught. So your theta is basically L over E naught over L over 3, so that is 3 E naught over L. And plugging back the value of theta, we get the vertical component of this force is 3 P E naught by L. Similarly, at the ends, as I talked before, the vertical component is P theta and the horizontal component is P, and the vertical component can be computed as, plugging back the value of theta, it is 3 P E naught over L. So these are the forces that will act on the concrete from the pre-stressing tendons. Now, so as you can draw the force action of forces on the concrete beam. So at the anchors, both anchors, there will be the horizontal force P, there will be the vertical force 3 P E naught over L, horizontal force P, and the vertical force 3 P E naught over L acting downward. And at the points of kinks, at the kink points, there will be the upward force 3 P E naught over L and 3 P E naught over L as well. So these are the forces transferred from the tendons on the concrete. Now, with this force condition, it is basically like a concrete being subjected to 4-point loading. So we can draw a bending moment diagram like this one. And as for this load conditions, your maximum moment M due to the pre-stressing force P will be nothing but 3 P naught over L, the forces multiplied by this distance, which is L over 3. So this will also give you the moment that created from the pre-stressing force as P multiplied by E naught, and this is negative as the forces are creating the hogging moment, so it is a negative moment. So this is the moment caused in the beam due to the pre-stressing forces or the equivalent forces. Now, if we consider more general profile and for the cable along curve profile, let's look at a small section of the cable delta X. For the small section length delta X of the cable, you can see that the force P is the pre-stressing force is P is acting at an angle of delta theta, and there will be force delta F acting on the pre-stressing tendon from the concrete, and similarly the similar force will be acting on the concrete from the tendon. Reaction force will be acting as well. So for this small cable length delta X, the curvature of the cable is delta theta over delta X, and the equivalent load on the short length delta X is the vertical force component of this force delta F is P delta theta. So this force will be acting on the concrete from the pre-stressing tendon of delta X length. So the equivalent force per unit length, due to this pre-stressing on the concrete is WP is given by P delta theta over the length delta X. So delta theta over delta X is nothing but the curvature. So the equivalent force per unit length WP on the concrete due to the pre-stressing wire in this curve profile is given by the pre-stressing force P multiplied by the curvature of the beam, curvature of the tendon, sorry. So the WP actually acts radially along the profile of the cable. So the WP will act in fact radially like this one, but for the small angle we can consider it to be acting vertically on the concrete. Now if we consider a parabolic, more specific curve profile, and we consider it as a parabolic profile, the equation of the parabola is ex equals to ax squared plus bx plus c, where ex is the eccentricity here and x is the distance from one of the support. So you can get an equation of the parabola from here, and to find the constant a, b and c we'll use some boundary conditions here. So the boundary condition for us in this profile is that at x equal to 0, at this point your eccentricity is 0. At x equals to L over 2, at this point your eccentricity is maximum, that is E max, and at x equals to L your eccentricity is 0 again. So if you plug in back all these three equations in this equation, you will get the values a, b and c, and that will give you the profile equation for the parabola like this one. Now if you differentiate this equation once, you will get the slope of the cable as given by this equation. If you differentiate it again, you will get the curvature of the cable. So the curvature of the cable, by differentiating it, comes at 8 E max over L square by differentiating it twice. Now plugging back this curvature into your previous equation, you will so as we saw in the previous slide, the load per meter length from the pre-stressing tendon on the concrete is given by the pre-stressing force multiplied by the curvature. So plugging back the value of curvature here, you get that the load per unit length on the concrete due to pre-stressing wire is given by 8 PE max over L square. So these are the forces that are acting on the concrete from the tendon. So these are the equivalent forces acting on the tendon, and of course we have the forces at the anchors here. Now if the external load is acting on the beam, so this the external load is acting on the beam, and the external load is W. So the moment due to external loading, it will cause a positive moment of L square by 8 here, and this is shear force diagram. And similarly, the pre-stressing force which are acting upward, so the pre-stressing force per unit length from the cable, these are acting upward, which is given by WP. And this force, the uniformly distributed force again, due to the pre-stressing, will cause a positive bending moment, will cause a negative bending moment of PE max, like this one. And we know that for the load of WP acting uniformly in upward direction, your negative bending moment is given by WP over L square, and you put in the value of WP here, 8 PE max over L square, we can get that the moment caused by this pre-stressing force WP on the concrete is PE max, which is negative moment, and this moment will counteract with the moment caused by the external loading, which is WL square by 8. And to achieve a balance condition where the pre-stressing load is balancing out the external load so that we don't have any deflection, these two parameters needs to be equal. So the PE max, that is the moment caused by the pre-stressing force, should be equal to the moment caused by the external loading. So for the design of the pre-stressed concrete beam, we can choose the load P and E max in such a way that the external load will be exactly balanced, so that there won't be any cracks or deflection in the beam. So the load balancing concepts refer to the introduction of pre-stressing force and choosing the pre-stressing force P and E in such a way that the internal equivalent load WP, that is this one, are equal and opposite to the externally applied load. So these are the internal loads that are acting on the beam from the pre-stressings, and these are if equal and opposite to the external loading that are acting on the vertical direction here, so it will have zero deflection and zero cracking. So in the balanced load condition, the beam will undergo only the axial compression because there is no bending. And for the given external load, designer can choose the pre-stressing force and the cable profile in such a way that load balancing can be achieved. And at the load balancing concept, there is no serviceability problem because there is no deflection and then no cracking, so the serviceability is automatically achieved. And however, during the transfer of the forces and during the excessive loading, full loading conditions, there will be some deflections as well, and we have to check for that one. So now to summarize it, when your external load W is smaller than your balanced load WP, there will be upward camber. So because the pre-stressing force is more than the external load, so you will have upward camber. And if the external load W is greater than your load from the pre-stressing WP, your beam will have a deflection, and there will be tensile stresses at the bottom. And when the external load is exactly equal to the pre-stressing load WP, it is called as the balance mode, and at this one there will be zero deflection, that's shown in the figure, and there will be zero cracks as well. So it is desirable to achieve a zero deflection in the breezes when there is no traffic. So what is usually done is that for a case of rural areas, the breeze is designed in such a way that when there is no large traffic going on the breeze is designed to be in the balanced condition. So when the tendon profile and pre-stress forces are selected in such a way that balanced condition is achieved, so the breeze will be in the uniformly stressed conditions for most of its life, so there won't be any crack appearing on it, and there won't be any deflection as well. But when there is a large load moving over the breeze, there will be some stresses coming on the beam, bending stresses coming in the breeze. But in the normal condition, when only the dead load is acting on the beam, there will be no bending stresses. There will be only uniform stresses acting on the beam, and there will be no cracks as well. So using this load balancing concept, we can choose P and E max, the pre-stressing force and the eccentricity, in such a way that it will balance the external load.